Hi everyone, this is Ashley Bedford, founder of the Runtime Diaries, and we are on day 22 of our hashtag 30 Days of Code Challenge with Educative. So today's problem is 𝗂𝗪 less than k. Let's get into it. Today, we're tackling a classic pattern that appears in all kinds of optimization problems. 2 pointers after sorting. The problem is called 𝗂𝗪 less than k, and it looks simple on the surface, but here's the twist. You're not looking for an exact match. You're looking for the best possible result under a limit. There's a beautiful pattern here. So let's dive in. Here's what we're given. An array of integers and a value k. The goal is to find the maximum possible sum of two distinct numbers that is strictly less than k. If no valid pair exists, you return -1. Here's an example. Nums equals an array from left to right, 34, 23, 1, 24, 75, 33, and k equals 60. The best valid pair is 34 plus 23, which equals 57, and 57 is less than 60. So this isn't 𝗂𝗪 in the regular sense. We're not trying to hit a target. We're trying to get as close as possible to k without crossing it. This problem is interesting because you have two competing forces. First, you want the sum to be as large as possible. Second, you must stay strictly under k. So there's this tension between exploring large sums and avoiding invalid ones. Brute force will find the correct answer, but it wastes an enormous number of comparisons. We want to do this intelligently. Let's start with the obvious baseline. You take every possible pair, I, j, compute the sum, and if it's valid, you store it. Classic double loop, O of n squared comparisons. This works, but it doesn't scale. If your array has 20,000 numbers, you're doing 200 million comparisons, and that's before even looking at the sums. So brute force gives us the structure, but not the efficiency. Here's exactly what brute force looks like. You initialize best to -1. When you use a double loop, for each pair of indices I and j, you compute the sum. If the sum is less than k, you update best to be the maximum of the current best and the new sum. After checking all pairs, you return best. Simple, clear, but expensive. Every pair is scanned, even when it's obvious the sum will be too big. The real issue is that the numbers are unordered. There's no guidance, no way to skip bad pairs. Every comparison is blind. What we want instead is a way to use what we know about the numbers to avoid unnecessary checks. This is where sorted arrays plus 2 pointers starts to shine. Here's the breakthrough. If we sort the array, the smallest values are on the left and the largest are on the right. Now we can use 2 pointers, one at the smallest value and one at the largest. Depending on the sum, we move one pointer or the other. This transforms the problem from random guessing to guided exploration. Here's the full 2-pointer logic. First, sort the array. Second, set left equal to 0 and right equal to n-1. Third, compute the current sum, nums of left plus nums of right. Now, there are two cases. If the current sum is less than k, this is a valid sum. Since we want the sum to be larger, we move the left pointer rightward to try a bigger number. If the current sum is greater than or equal to k, it's too big. We move the right pointer leftward to try a smaller number. Every pointer move is intentional, and there are no wasted checks. Here's the whole algorithm. You sort nums. you set left to 0 and right to the length of nums minus 1. You initialize best to -1. Then, you enter a loop that runs while left is less than right. Inside the loop, you compute the sum of nums of left and nums of right. If the sum is less than k, you update best to be the maximum of best and the sum. And then you move left rightward by 1. Otherwise, you move right leftward by 1. After the loop exits, you return best. It's elegant because everything is conditioned on a single comparison. Is the sum less than k or not? And here's the clean Python implementation. You sort the nums array. You initialize left to 0 and right to the length of nums minus 1. You initialize best to -1. Then, you enter a while loop that runs as long as left is less than right. Inside the loop, you compute s as the sum of nums of left and nums of right. If s is less than k, you check if s is greater than best. If it is, you update best. Then you increment left by 1. Otherwise, you decrement right by 1. After the loop completes, you return best. This solution is easy to reason about, and it performs extremely well across all input sizes. Let's talk about efficiency. Sorting takes O of n log n time. The 2-pointer scan after that is O of n. So the total time complexity is O of n log n. The space complexity is O of 1 if we sort in place. This is significantly better than the brute force O of n squared approach. Let's walk through a concrete example. Nums equals, from left to right in the array, 10, 20, 30, 40, and k equals 50. After sorting, the array is still the same. We start with left equal to 0 and right equal to 3. The first comparison is 10 minus 40, which equals 50, which is not less than k, so we move right leftward. The second comparison, 10 plus 30 equals 40, which is less than k, so we update best to 40 and move left rightward. The third comparison, 20 plus 30 equals 50, which is not less than k, so we move right leftward. Now, left is no longer less than right, so we stop. Best equals 40. Every move is purposeful. This approach handles all edge cases naturally. No valid pair? Return -1. K is extremely small? The logic still works. Duplicates in the array? No problem. Already sorted or reverse sorted? It still works. Tiny arrays of size 2 or 1? They're handled gracefully. The 2-pointer logic handles everything. Here's what I want you to take away from this problem. First, when sums depend on ordered values, sorting unlocks structure. Second, 2-pointers eliminate brute force redundancy. Third, every pointer movement has meaning. Fourth, we upgrade O of n squared brute force to O of n log n. And fifth, this is a core algorithmic pattern worth mastering. You'll see this pattern again in threesum, threesum closest, container with most water, twosum and sorted arrays, and almost every sliding window variant. This is one of those gateway problems that unlocks many others. And that's a wrap for day 22 of our hashtag 30 Days of Code Challenge with Educative. If you like this video, like it down below, share it with a friend, subscribe to our YouTube channel. We'll be bringing you much more breakdowns of different LeetCode problems shortly. We'll see you soon.